Okay, let's start the exercise part. So, the exercise 3 is about system responses and signal spectrum. And basically, the first question is about the same as you had already, the second exercise. So, finding the system parameters from this graph. And then stem plot the first 12 values of the impulse response. So basically use this system, determine the parameters, and run your impulse through a system implementation, which in MATLAB will be filter. Okay. And then plotting the frequency response at certain sampling rate. Then there are some questions about linear or nonlinear phase response. Zeros and poles on Argon's diagram. Okay, figure and at which frequency the system has highest attenuation, physical frequency. Okay, then the group delay, plotting the group delay. Then scaling the system such that it has unity gain at passband. So you don't have a magnification of the signal, so that at some point will start saturating. Okay, that's quite common on the filter, that you if you don't need amplification, then you don't have it. And then the last one is basically the combination of, well, the first one. So you will have again some random noise with signal to noise ratio again. Excellent. So now you need to, if you didn't get this signal to noise ratio right on the first exercise, this is the place to correct it. Okay. And then calculate the spectrum of the last. So single spectrum of the last 2048 data points. And the spectrogram. And filtering sound sample and calculating the spectrum of filter data. So basically first do the signal, then some spectrum of it, then filter it and compare those spectrograms. Simple things. Okay. I'll try to do something similar to this one on my show, but I will have a little bit different starting point, just for fun. Since we have this beautiful filter, 4-point running average, best in the world, not quite. But anyways, that's the original form, and then I already modified a little bit by putting some poles outside of the unit circle. Okay, so I'll try to basically set up a system like that. Calculate the system parameters. Yes, you have a question. It doesn't show up. Not quite. Okay, let's see if it's a little bit better. Good. This is the cheapest camera I could find. The best we can afford. All right, so basically how to calculate the system parameters from zeros and poles. So simply, first I need to set up the zeros, Z1, Z2, Z3, and those are actually I, Z2 is -1, and Z3 is -I, or J, whatever, it's the same thing. Then we have 3 poles, pole 1, pole 2, pole 3. Oh right, that looks like, oh, that's nice, it's about 50-50, right? So pole 1 is half plus half of I P2 is plus half plus 0 I P3 is half minus half I. And those are complex conjugate pairs, as well as those are complex conjugate pairs. And then in addition to those, if we have these single poles or zeros, they must be on the real axis. Now, when we are doing the calculations from these, we will always get a real factors for these, real parameters for this system. Okay. So now we can actually do the h of z. And only thing which is missing is the gain. We don't know the gain yet. But that's one part, is to find a gain so that we will have unity gain in passband. Okay, so we have P1 minus, Z minus P1 times Z minus P2 times Z minus P3, and downstairs Z minus. Now, why nobody actually told me that these are not P's, these are zeros? Why didn't it? Your fault. Okay. Z minus P2, Z minus P3. Okay, there we go. That's the transfer function. And from that one, if we calculate the sum form, we will have actually the, well, bk times z minus k, ak times z minus k, and here we have some scaling factor c. All right, so let's calculate this one. This basically, now we have a fact that we know the roots of the polynomial, how to calculate the corresponding coefficients of the polynomial, and that actually is done with the function poly. But for that one, we need to have these actually vectors like I minus 1 minus I. Same thing here. So not row vectors, but the column vectors. All right, then I'll start the MATLAB. Ooh. Excellent. Now I have the MATLAB. Good. Or, well, move that a bit like that. Ooh, that almost shows up. Excellent. So, now we are on exercise 3. Let's see if I can actually... There we are, and then basically I'll first go directly and define the zero locations and pole locations. So z equals 2 I, and then using semicolon that actually ends the line, right? So the next one will be on the next line. Minus 1 and minus I. Okay, that's a column vector. Poles, it has a common multiplier times 1 plus 1 plus I, 1 minus I. Right, yeah. Those are the coordinates, complex coordinates of the zeros and poles. No magic. Then we do some magic by calculating these coefficients. Corresponding coefficients. And first the numerator coefficients. Numerator coefficients are one, 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 one. Yes, of course. Those are the same coefficients as you would have for 4-point running average. Only the scaling factor is missing. And for obvious reasons. From this picture you cannot see the scaling factor yet. So fundamentally the scaling factor would come here. If you took Manfred Junke's class, you would recognize this as the Argand's diagram. And there you have the magnification, or the amplification, the total gain of the system. Okay, but we'll find it eventually. So numerator coefficients, or the multipliers of the input term, and then the denominator coefficients A equals polynomial of P there. That's nice. Easy to remember numbers, and as you can see they are all real numbers because I selected complex conjugate pair. Good. So A and B are there. Now we can do some other things like, well, just for fun I will check if this is the system where I started. Z-planes, checking, and poles. Z-plane. Yeah, wow, that's cool. Looks even better than I draw there, which is almost impossible, but okay. Then another one, maybe we could be interested on the frequency response. Okay, frequency response in here is frec response. Okay, it has plenty of different uses. If you take a documentation of the frequency response, it actually shows you that, well, you can just have the complete filter parameterization on one single structure called hfilt, and it does everything. That's because of the this filter design toolbox has definition for that kind of structure, and that you can use it if you wish. But I'm an old guy, so I use that version. Let's see more help. Help. Okay, it doesn't show it here. Just okay. Yeah, actually it's it's not here. It's on the different package. This is one of the funny things about the MATLAB. This fast help actually shows only the more advanced function. There's also the exactly the same function on a basic MATLAB, which has different parameters. Okay, so but anyways, the third term would be how many points you want to calculate it. So how many points on half circle to calculate the frequency response. For example, if I wanted 1024 points, that would be just fine. If you use hundreds of points, then you probably see a jagged line. But with 1,000 points, around 1,000 points, you will get smooth lines. If you need more details, just add points. Then the fourth parameter is sampling rate. If you know the sampling rate, then you would actually use it here. For example, 1000 Hertz. So there. Wow, that's cool. Almost flat response on passband. So it's a low pass filter because there's attenuation on the higher frequencies. So it's attenuation of about 10 dB, but here we have about 25 dB amplification on the passband. So 25, 10, 32 dB. Not drastically excellent filter, but still much better than just that running average. On the amplitude response, it has almost flat response. Almost. If I would move that one a little bit that way, then it would be even flatter.
The flat response is in the beginning.
Yeah.
But if
Yes,
you're
yes,
interested in
this
low
one.
frequency signals at some frequency
Yes,
range.
flat response on passband. On passband. Next week I'll be out. Okay. But anyways, I think we'll discuss it later. But anyways, there's when we are going to filter design, then there's the different areas of filter what they are. So basically, the passband is the band you want the filter to pass the signal, and stop band is when you want to attenuate the signal. And here we basically have more the gain here and more attenuation here. I should zoom it a little bit. Let's see, where is the zoom?
Kind of looks more like a backstop almost, but
Yeah, it always has some of that
yeah. Okay.
behavior because of those notches here.
Yeah. Okay.
Yeah, those frequencies. Attenuation goes to infinity.
Yeah.
All right. How do I get the? Oh well. Anyways, that was the frequency response. What else? Let me take a quick look at here. Oh yes, the impulse response. Impulse response. And for that one, we need an impulse. Impulse. Impulse response. First, we need some indexing here. For example, -2 to 14. I started from minus something because I want to see also the moment, couple of moments before the filter starts, just for that reason. So that's the just indexes. Then the delta function, simply that one hits 0. That's the impulse function. And then the impulse response is the system response, which is always like that when input is impulse. There. That's the impulse response. And just for fun, let's stem it. Stem in HH. There we go. So that is the impulse response. And now the question is this FIR or IIR? What do you think? Does it stop at the 14th point?
Yeah, it seems that it stops.
Yeah, but you don't need to look that far. There's a trick. Actually, if it's a FIR system, you take a look at how long those system parameters, vectors are. And you basically define the order number from that. So now this is a third order system, which means that after this third point, it should go to 0. But now it doesn't go to 0 here, so it's infinite impulse response system.
So it just goes so small in the end that
Yeah.
it's hard to see there, but it's
Yeah, it goes.
forever,
Yes.
but really small amplitude.
Yes.
Yeah.
Within the calculation accuracy. All right. So let me mark here. Infinite box. There is no zero signal after the nth delay or time step. Yes, time step. Where's the n actually is? Order number of the system. That's actually also the highest order delay. Supposed to be. If there's anything after that, then it's IIR. Yes, excellent. So that's an IIR system. Good. We took a look at the zeros and poles, also the frequency response. How about now let's take another look at the frequency response. And then the other part is, guys, turpa kiinni siellä. Joo, mä oon hyvä aina vihjaamaan. Okay, so phase response, and well, that already shows it's non-linear. This is not a straight line. But then we also should take a look at the group delay. I don't just remember what was the name of the function to calculate the group delay. I should take a look at the documentation. Ooh. Group delay, but let's see if it finds. This is a DSP system toolbox. That's on group delay. I think that's functions. Okay, GRB delay. Group delay, then the filter coefficients. Excellent. Richard's group delay based. Well, we'll see. We'll see, does it also work with the old-fashioned way. Group delay B A Let's see, does it give anything by that? Yes. That's a group delay. Normalized frequency. So that's the sampling rate over 2. Okay, just a guess, but that actually might be. So if you put that number of points and then the sampling rate, you get the physical frequency here. All right. So basically. It has 2.5 samples delay on the beginning, then the delay is more goes higher, and then it goes lower on the stop band. So remember, the pass band was here, so it's fairly good on the group delay for any frequency below, well, maybe 50 Hertz or so, but then it starts to distort the signal shape. if it matters. Okay. On a voice sample, sound samples, absolutely no matter how much you put there group delay, as long as it's not, the non-linearity is less than 10 milliseconds, you cannot see it or hear it. Remember the voices. Even this air actually has non-linear behavior on phase response. Different frequencies are traveling different speed on the air. Okay, that's non-linear media here. So why it would actually matter anything on the sound overall? Maybe you can actually make a certain kind of long distance effect using that. Thunder. Yep, thunder a few kilometers away actually has already, say, 1 second time you get already, say, 10 millisecond or 100 millisecond difference between different frequencies, which you already can detect. Human ear is good for 10 milliseconds differences. Okay, 10 millisecond difference, you can already start hearing it. I know it only because I was playing in a band. Never put the loudspeakers, spread it like that one, unless you have some phase control and put the sound that way. But if you put a 100-watt speaker here and another one there, it sounds awful. It sounded awful also that because I couldn't play well. Okay, so group delay. Yes. So frequency response, amplitude response, group delay. Now we need some voice. I think we need some voice. No, we need to scale the filter. Since we still have the problem with the I want this one to be at 0 dB. So now I have 25 decibels of amplification on a signal. That's a lot. I want that one to 0 dB, so it does not disturb the signal that we want to pass the filter, but only attenuate this stop band signal. Easiest way to do this one is by brute force. All right. This is the brute force approach. I will calculate the frequency response. So if you put a variable where to save the frequency response, then it actually just does the calculations, and it gave me 1024 by 1 complex vector here. And that's my frequency response. Just a graph in complex numbers. So it has also the magnitude, and then it has the phase. Yeah, that's good. Since now I could basically separately plot the amplitude response and the phase response, or I could just do the brute calculations of maximum of absolute value of, so maximum of amplitude response calculated in 1024 points. This is engineering, this is not science. This will give me good enough value to use on the calculations. So that's the max amplitude response there, which is, by the way, that's nice, it's 16. Well, it does actually make sense because, well, I had these the scaling the vectors here, one minus 1.5, and then the last one was 0.25 or something like that. Sounds like, divisions of 2, more or less, and then the other one's 1, 1, 1. So that's 20 some decibels. Yes, 10 times signal is 20, and then 6, so it's 20. Yeah, it's actually about 25 decibels magnification, and now we just need to divide the numerator parameters by that number. So that one here actually would be 1/16, and it's best to use that one for those parameters, numerator coefficients. Why? We want to keep the A1 or A0 as 1. We don't want to touch that. Since the A0, the first element here, there is the multiplier of y of n, the value that you are calculating. Okay. So the scaling would be simply SC equals BB divided by CC. And now using that parameter, now it looks much better. So it has unity gain on the pass band, and there we see about 30 some dBs of attenuation on the stop band. The minimum attenuation on stop band is about 30 dB. Excellent. So now we have a system filter. Next we could do some spectrograms. Let me first produce a signal and some noise on it. Spectrum. Signal, for example, okay. Sampling rate. I want to use that as a sampling rate. Then have a sampling time vector. This can be also done so many different ways, but this is my favorite way. So I start from 0, go 1/f steps. Oops. That's the step size, and then say 1 second. So this is 1 second long vector of times or sampling times. Then I do, for example, signal like so amplitude 0.5 times sine 2 times pi times. Are there anyone who is playing any instrument anymore? 440 hertz.
That's an A.
Yes, not A plus. Just plain A. All right. What is C?
I don't know.
I do. Okay.
Probably depends on which octave too. There's more than one C.
Yeah. But the basic C. Okay. 2 times pi times 440 times 2 to power of. In how many notes is 1 octave divided?
Hmm?
How many notes are in 1 octave? Half notes.
Half.
12.
12.
12. Yes. C. A. Okay. How many half notes are in between A and C? 4.
4.
3. No, it's
No, that's a minor third, so it has to be a 3.
3. No.
Please.
A sharp, B, C. So
A.
it's
C.
delta
Yeah.
4.
3.
Yeah, 4.
It is.
Yeah, 4.
Yeah. What? No.
3. Yeah.
No,
Yeah.
4 is a minor.
Yeah.
it's a
Okay.
major third. That's a minor
Okay, good.
third.
I take your word on it. Okay. C. That's C. So it's just basically at the on amount of half notes. Oh,
It's
okay.
actually that simple, huh?
Yeah. Yes. Now you can make your own music. It'll sound so crappy. So it's mathematics, you know. Oh boy. Yeah, on this scale. So, whoa. So let's add those together. Yoo-hoo, this will be so much fun. Some noise on it. So our signal will be SS plus SSC plus some noise, random numbers of the size of SS, for example, times. Well, that's quite a lot of noise, but it doesn't really matter. Let's have that lot of noise there. So we still should. Whoa, SS. It was your fault again.
Just thinking of what happened.
Yeah. Okay. Good.
440 is pretty close to 500.
Yeah. So, sit and then how does one sound like? Sound SSN and FS. Hey, you can still hear the tones there. Wow, that was fun. So that how it sounds like. How about how does it look like? Okay, well, there are two ways to look at it: spectrum and spectrogram. Let's do the spectrum first. And single spectrum, meaning that first you have to set up the point of interest there. Since, well, we could do the the full, how many points there are, 44,000 something points. I don't want to do that. I just take, for some reason I fixated to 1024 points. That's a quite nice number. So I take that many samples of that sound. So SS. Okay, that's sample, or SSA. This would be first 1024 points. You can always put an offset to that one SSN, say that 1 to 124 plus the offset. Okay, just as a hint to your question 9, I think. All right, so that's just one part of the signal. It looks really crappy. I don't even show it. But what I'm going to do is to calculate the spectrum using the Fourier transformation. So FS would that's FFS. FFT of SSSA. That was snappy. Well, up to 1 million they are all snappy. In good old days, you needed to wait for a while to get that 1000-point FFT. Good old days. Okay, so that's the Fourier transformation, but this is not yet the spectrum, power spectrum. To get the power spectrum, you need to multiply that one with a complex conjugate. So that was the FFS dot times complex conjugate of FFS. So this is the power spectrum. All right, not yet. When you plot it, it has to be in dB. So how do I multiply this one? It will be inside of log, of course. So log 10 of PFF. But what is the multiplier? 10 or 20? 10 or 20? Which one?
20.
No. Guess the other one.
If it's power spectrum.
It's power. It's already power. So FFT is basically still on amplitude scale, but when you multiply it with the complex conjugate, you get into the power scale, and that's actually the power. Okay, it's not the calibrated power. It's just dB, which means that you can rescale it any ways you want to. So you can actually scale it so that it shows the decibel bits, but I don't see a point here. So basically the most important part is here to get the actually the power and see how it changes. Where are the most of the power? Well, decibels is relative scale in any case. Okay. Next we should plot it. I'll just plot it like it is to make a point. dB PFFS. And let's see. And as you can see, we had the let's go on the word of FFS. So FFS was a complex number, but then we went to the PFFS. It's double. Well, that's because you had the number multiplied by a complex conjugate again. So you get real numbers. All right. It looks like that. Something funny on this picture. It's symmetric. And the middle point is at 512 points, or actually 513 to be exact. So what happens on this mapping on the Fourier transformation, especially for radix two-form Fourier transformation, basically it maps only the positive side. But of course, this is still the same as the negative side. So our first half of it actually is the spectrum between 0 and Nyquist frequency. The rest of it is just a mirror image on the other side of the Nyquist frequency. Okay, so in that sense we need only n divided by 2 plus 1 value to actually show the complete spectrum. Since half of this is redundant information, we don't want that. But let's first do the frequency scale. Frequency scale, so do we already have FF? Maybe. No, we don't have FF. So our frequency scale, FF, has 1024 points. The same amount of points that I had on the Fourier transformation. So 1024 minus 1. The first bin there is actually for DC, frequency 0. Starts from 0. All right, so we can do it by hand like that or do some calculations. But anyways, that's how many points. All right, and then the frequency resolution. Yeah. Times something, right? Sampling rate divided by 1024. So it's just linear scale. There we go. Now we can plot it again using just half of the values. So FF from 1 to 513, and also those 1 to 513, only those first half point, and that's the full spectrum. And there you could actually also stretch the axis so that it looks nice. Anyway, let me pop it out a little bit. Let's see which configurations. Let me undock it. So let's zoom a little bit. And dock it again. So our frequencies were 440 hertz, roughly here, not exactly, because we have the actually fs over 1024. This has 43 hertz resolution. See, if you need better resolution, you need more points. Okay. 1 hertz requires 1 second long sample. 10 hertz would have 100 milliseconds of the length of the sample. So more resolution you need, the only way is to just add some more points. We are not going into the super resolution by doing the correlation. It can be done, but anyways, it's out of scope. Anyways, so those are the 2 signal peaks, and then let's see, can I get it? This is so frustrating. Why it doesn't show me the there. Okay, this is the full picture again. There, so we can actually also see that this is why we are hearing those tones, is because their spectral power on these frequencies are so much higher. They are actually 20 dB higher than the noise floor here. And the noise, well, I added basically, there's more noise than signal here. And you still can hear those tones. Okay, that's actually quite nice thing for 2 good reasons. If you have basically a wideband spectral noise, it means that, well, with a really simple filtering you can get rid of it. Okay. And the other would be, well, it's nice to hear some music instead of a noise. All right. So, and what happens if I calculate the spectrogram then? What do you think? More? Spectrogram. Let's calculate the spectrogram. Unfortunately, this spectrogram is made by mathematicians, not engineers. I'll show you what not to do first. Okay, there's that signal. Now we use the full signal. The spectrogram is a series of spectra, signal spectra. So the whole picture as a function of time. And our signal was SSN, right? Window. Actually, that will be next topic, either next or following week. The window shape, different window shapes can be actually used to do some filtering of unwanted effects due to those edges. But then there's a number of overlapping, meaning, okay, I think I need to draw a picture here. So the full signal is something like that, very long. Then you take basically a window that defines the which part of the signal is under observation. Okay, so that's the window. If you just put a width of the window in samples, then it's basically a square-shaped window. Then there's a number of overlaps. So basically, the next window would start wherever you want. One would be to have it starting here, but on the other hand, usually this window has some nasty effects here. Or if you want to see, basically, if the signal changes in between, you probably want to see the transition there. So basically, the window, the overlap would be that one. how much you would put overlap between those samples. Now I lost the help. And then number of FFT points there. So how many points you would like to have in your Fourier transformation. You can select bigger one than window, which means that the rest of the data would be zeros. You will gain some spectral resolution, but you don't gain any information point. Or you can actually put the this number of Fourier points in Fourier transformation the same as window. But you can play with these numbers. What then? Yeah. Then the next one would be sampling rate. If you compare sampling rate, the same way as in frequency response, if you put their sampling rate, then you see the physical frequency scale. And physical time. Time in seconds, frequency in hertz, if you put the sampling rate. Then you need to put one more parameter, which is not here. It's in here. At the end, we have to actually define also their y-axis. I will show you why. This is so stupid. Step spectrogram window size. Now I use 512. Overlap half of it. Then number of points the same as window width. Then the that was it the sampling rate. What else? Then y-axis, maybe. Help of selection. Window overlap NFT FS. Yes, there. Without that last parameter, it looks like that. What do you say about the time that starts on the bottom and grows up? What? It doesn't make any sense.
That's pretty nice. I think this is the only way you can do it.
No, that's awful. That's the worst. In which culture ever storytelling starts from bottom and goes up?
Yeah.
Okay. In mathematicians, yes. Mathematicians have done this one for us. But anyways, fortunately, with the pressure of plenty of engineers, there's also the fourth command, the parameter, y-axis. That's how you would like to have it. Time from left to right. The frequency from bottom to top. You got some music there. Excellent.
Finally found a real use for my one.
Yep, yeah. Good. Next you want to put some attack and decay and other components there.
Yeah, that's...
Look at the old Moog synthesizer, actually. You can do every single function of Moog.
Yeah.
Quite
and
simply.
this is like, now it's just sine waves, so
Yeah,
it's
yeah.
not really that exciting.
Yep. One person converted. Welcome to
Making
the
like
dark side of the force.
Making a super saw with like 7 saw waves that are out of phase and out of tune with this sounds like a real pain in the ass. So.
Yeah, yep. Okay, but anyways, so that's the spectrogram. So the time goes from left to right in milliseconds and frequency top to bottom in kilohertz, and this basically information is in color color coded here. So it's mostly noise, yeah. But then there are those two tones are right here. Actually, they are overlapping because of the sampling. Sample size was 512 points, which means almost 100 hertz. 100 hertz the bin for that information. Okay. And the last thing to do here, what does it look like if we filter this?
What was the sampling rate for this, the FS? How big was the sampling rate?
44.1.
Ah, okay.
Yeah. Yes. I hope. Oh yes, it was. Yeah. Yes. All right. Let's do some filtering. So we had the system somewhere on the beginning. So A and B's are there. All A and B's SC. Filter.
Wait, no, that's
Huh? What?
no, I'm
Oh.
kind of thinking out loud. More like
Yeah, okay. Filtering this signal with system
what's the problem?
BBSC AA. There. SSF equals filter BBSC. Remember that filter? It was the that one with scaling factor. Yeah, the with 1/16 scaling factor. Okay. AA. What else? The signal. As I said, this could actually do something for this sound, I think. Okay, so let's first hear it. So the that was the original one.
It's low passed, at least somewhat.
Yes, and less wide spectrum noise, or the high frequency noise. But seeing is believing, so let's do the spectrogram of this signal. SSF on different figure. Ha!
And that's, I guess, the huge dip in the.
Yeah. Yes.
That makes sense then.
Yes. So it took some of that noise out because these signals happen to be on the passband. Yes. The first time ever this demonstration works. This is a good place to stop while I'm still winning. So yeah, the third exercise. So just start doing it. I'll be here until 4 o'clock again. Okay, good. Thank you.
Ai laitat sun nimet väärin. Anteeksi.
Ei saa tätä enää takaisin.
Ei mä kahta tota.
Onko se tän kirjastosta?
Joo. Siellä on olemassa semmoinen vanhempi.
Toi oletettavasti tää